Okay, we're talking about the holes versus asymptotes ditto, and in the back of that packet you have a notes page. So I want to go to that first and take a look at the piecewise graph that's there. Now we've already had the piecewise limits on our SIG test, and I want to talk about the ones we are going to do today that come from it. We've already done the infinities, that's A and B on this sample. If you look at letter C, that says find the limit as x approaches 1, and if you look at 1 over here, that's the asymptote. So we are going to talk about the asymptote today. Also, I wanted to look at G and I. G is asking you to find the limit as x approaches -1, which is just that guy there, which nothing fancy is happening, and 8, which is here, and nothing fancy is happening there. So in those two locations where nothing weird is happening, I'm going to refer to as an ordinary dot or a Joe Schmo or something that's just very simple and not confusing. The other location I want to talk about today is the -4, which for us is right there on the piecewise graph. Now the answers to all of those I hope you already know. But what we're going to do is analyze these three types of locations when you're given an equation and not a piecewise graph. So let's talk about what we know already just before we leave the piecewise graph. We know that the limit at an asymptote we write does not exist. Normally we do a support proof for it, but for now we're just talking common sense. We know that the limit at an asymptote does not exist. The limit at an ordinary Joe Schmo location, like that dot right there, is just the y value of that dot. So we would have wrote -3 for this one. The limit at 8, which is this location, we would just give the y value of that dot right there. They're just ordinary locations, so the y values are the limits. We would have wrote 2 for that one. This guy right here I'm going to call a hole today. So that looks like a hole in the graph. Now, the way we did holes for piecewise graphs, we did a proof coming from the left and coming from the right. And coming from the left, we would have been heading towards the y value 3. Coming from the right, we would have been headed towards the y value 3. And since coming from both directions have the same result, 3, then the limit is 3. So what we need to get out of this is this y value of the hole is the limit. So if we could figure out the y value of a hole from equations, we'll know the limit at that location. So ultimately that's what we're going to do, but now you're just going to see an equation. So basically, when you're asked to find the limit at a number, it's going to be one of 3 scenarios. It's either going to be an asymptote at that location, which I'll abbreviate, a hole at that location, or an ordinary point. Let's just call it an ordinary Joe. I don't have a clever name for that. So it's going to be one of those 3 scenarios. Now, an asymptote is created when an x value makes the denominator 0. So if I plug -1 into this x right here, I'm going to get 0, and we know divided by 0 is an error, and an error is something bad on our graph. It's not an ordinary Joe, it's going to be an asymptote. If you take a look at this thing though, however, this top factors. It factors to x plus 3 and x plus 1. The bottom is also x plus 1. And now we can see that this right here simplifies with this. If you were to graph this equation right here before you even simplify it, it would end up graphing a straight line that looks something like that. Something that has a y-intercept at 3 and a slope of 1. What's weird is this doesn't look like it would be a line at all, but it does graph a line because this cancels. Now, if you were to plug -1 into this, you would get an error. But if you plug -1 into this, which is just x plus 3, you would get this y value right here. Well, that y value here is an error, but because it canceled, that creates on the graph a hole. Now your graphing calculator has the ability to graph that, but it's really not that important. You just have to recognize that that's a hole. So, long story short, it creates a hole on the graph if it cancels from the equation and is removed from the denominator, which is what happened here. This x plus 1 got canceled. It still is there. You can't ignore the fact that it was there in the original problem, but because it canceled, it created a hole rather than an asymptote. Now, let's see if I can clarify that with the second equation here. Here, this is asking you to find the limit as x approaches 2. Now, 2 doesn't make the bottom, the denominator, 0, which means it's not an asymptote. The x plus 1, since it's the same equation as the one we just did, will cancel, which means we have a hole at this location, and this location would be -1, because -1 makes that 0. But when you're asked to find the limit at a location that doesn't make the bottom 0, that just means it's an ordinary point. And the limit at ordinary points are just the y values of those points, of that place, I should say. So to find the limit at an ordinary location, you just plug 2 into the equation. If you plug 2 into this equation, which we remember is this graph, basically we are finding this y value right here. Well, if I use this equation right now, I would get 2 squared is 4, plus 4 times 2 is 8, plus 3, all over 2 plus 1, which is 3. 15 over 3, which is 5. So the answer to this problem is 5. So to find the limit at an ordinary point, you just plug it into the equation. Now, let's say you simplified this equation to start. You recognized that x plus 1 simplified, you crossed it out, which created the hole, and the only thing that was left was x plus 3, and you wanted to work with this equation and not this one for this problem. Well, if you plug 2 into this, what are you going to get? 5. Same answer. So it doesn't matter whether you use the equation that still had the hole in it or the equation that had the hole taken out. When you're trying to find the limit at an ordinary dot, it doesn't matter which equation you use. The third situation here, this equation, the third equation, this is asking you to find the limit as x approaches -2. -2 makes the denominator 0, and when it makes the denominator 0, it's going to be one of these two things, an asymptote or a hole. It's a hole if that x plus 2 cancels with the numerator. Let's see if it does. So we factor the top. And we see that that x plus 2 won't cancel with those binomials up there. And since it won't cancel, and it stays in the denominator, it's an asymptote. And we know the limit at asymptotes is simply does not exist. That's all we need to do. Show that that guy's not in there. We did that by factoring. And since it didn't cancel, it's an asymptote. The limit at an asymptote does not exist. This really isn't a scenario we need to worry about. It happens a lot, though. This is asking you to find the limit as x approaches 1. 1 does not make this denominator 0. And if it doesn't make the bottom 0, then it's not an asymptote and it's not a hole. That makes it an ordinary Joe point. Now, I put this on here just because this happens, and I don't want you to freak out. We factor the top. The bottom was that guy. Since it's an ordinary point, to find the limit at an ordinary location, you just plug 1 into the equation. Now, I could plug it into here. I can plug it into this simplified equation. So if I put 1 right there, I get 2 times 4, which is 8 over 3. 8/3. Just an ordinary point, but fractions are okay. And the last one here, do I have time? I don't. We'll conclude this.